How does a museum piece hold secrets for advanced designs of icebreakers? That's a puzzler. Hello everybody, I am Nick the Naval Architect. Some time ago, I was on vacation and encountered this beautifully preserved old ship, the Coast Guard icebreaker Mackinaw. Her official designation was WAGB 83, because the Coast Guard likes to reuse the name. The Mackinaw operated on the Great Lakes from 1944 to 2006. She's an old girl that had a long and well-renowned life to her. During that time, her primary mission was breaking ice and protecting maritime trade. Here's the interesting part. We're talking a vessel in 1944. This is a World War II era vessel that still holds a lot of technological designs that are applicable today with modern icebreakers. Yes, technology has changed a lot from 1944, but this vessel still holds elements that we see in modern concepts for icebreaking. In the battle of ship versus ice, she shows how you crush your way through an ice pack. So let's see how old ships and new handle breaking through ice. A quick disclaimer though, icebreaking is very much a specialty in the world of ship design. I have some experience with icebreakers, designing ice-class cargo ships and working with an Antarctic cruise ship, but there are definitely specialists out there who know a lot more about this than I do. And if you encounter one, listen to them. First step to breaking the ice, we need to understand what is ice. Know the enemy. Because we're not talking about the ice cubes that you find in your refrigerator. We are talking about dense packs of sea ice stretching for miles on end. It can be shockingly strong. One study tested samples of sea ice, and they found that it had a compressive stress of 1 to 3 megapascals. Strong and clever. Ice packs are not a static thing, floating motionless. They're driven by winds blowing across miles of ice pack. The ice moves, it shifts, it builds up massive compressive forces within the ice pack. Those forces threaten to crush any ships that happen to be in there. Even worse, the ice doesn't disappear when we crush it. It slides along the hull, generating intense friction. Enough friction to pinch a vessel and pull it to a stop. And don't forget, there is always more ice. Remember, sea ice exists in freezing temperatures. What happens to water in freezing temperatures? Every time you break ice, you expose more clear water, and the cold immediately starts to make new ice. Ice breaking is a constant battle where we need massive strength to initially break the ice, but then also a smart design to deal with the friction of the ice as it runs along our hull. So how do we go about this? Do we go out there with dynamite or massive chainsaws or maybe just a gigantic blowtorch? Nope, not at all. The best method for ice breaking involves a wedge and lots of weight. The ship hull uses a very shallow rake on the bow. This is designed like half of a wedge. It's like a ramp that they can then use to ram that wedge into the ice pack, and the bow will slide up on top of the ice using that shallow rake. And once we're on top of the ice sheet, the massive weight of the icebreaker crushes down, breaking the ice. The Mackinaw used a pointed bow, following the traditional idea of a wedge. And this represented the pinnacle of science for her time. But more recent research has refined that. We found that the pointed shape led to extra pinching on the side, which increased the ice friction. So current designs favor a wide spoon-shaped bow. The idea is to try and reduce the ice friction and have all the forces pointing upwards to easily slide up on top of the ice sheet. Now, I wouldn't be a true scientist if I just dismissed all the other methods of ice breaking. A lot of people have asked me, why do we still do it this way? There has to be a better option. Maybe we should melt the ice. Maybe we should cut it with a saw, use explosives, or maybe cut the ice with high-pressure seawater. Remember, we have to break miles and miles and miles of ice. So you're going to try and find the most efficient way possible to do that. And in that case, it turns out that just slamming at it with a wedge is still the most energy efficient method. But let's just take a quick comparison here to show you the difference. Let's say we tried melting the ice. We're not even going to melt the whole thing. We're just going to use some heat to weaken the ice. Well, it turns out that ice requires an unusually large amount of heat to melt. So for context, the propulsion motors on the Mackinaw, they delivered 7.5 megawatts, 10,000 horsepower, of power for ice breaking. Now, if we instead chose to just melt 1/3 of the ice that she breaks in her path, that would require about 4,476 megawatts of power. You heard me right. 600 times more power than what the Mackinaw currently has. Well, we're past efficiency. You simply can't fit that much power into a ship this size. They don't make engines that good. So driving on top of the ice is the only way to do this without inventing some miracle power source. That doesn't mean that we've stopped innovating. People have experimented with other methods, but those methods mostly focus on reducing the friction of the ice as it runs along the side of the hull. Ramming with the bow still proves the most reliable method for initially breaking it. Speaking of disproportionate items, look at these numbers! Only 15% of the viewers are subscribed to this channel. Now, I understand that you have your reasons, but my cats, they're very disappointed. They depend on those subscribers for their kibble, or at least that's what they believe. So please, subscribe. Do it for the kittens. They need you. Right, back to ice. So we've broken the ice, but it didn't disappear. Instead of a solid sheet in front of us, we're now stuck with several chunks the size of a car, and these are all trapped underneath the hull. Remember, ice is buoyant. It floats upwards, collecting at the sides of the hull and piling up into the existing ice pack. This buildup drastically increases the side pressure and friction on the hull. So we need a way to remove the ice, clear it away from the ship. And this was so well understood that even in 1944, they had some innovative methods. The Mackinaw used a bow propeller. That's right, she has a propeller up at her bow, plus 2 at the stern. This bow propeller adds to the forward propulsion, yes, it does help, but its main purpose was to clear away ice from the bow. You've got all of the wash from the propeller pushing water and ice quickly along the sides and bottom of the hull. Now you might be thinking to yourself, wait a minute, a bow propeller? I thought you said that was the area we were ramming into the ice. Well, you're definitely right to be concerned there. First off, they never actually ran the bow so far up as to actually get the propeller onto the ice. We're not doing that type of a ramming action. But even so, that bow propeller is spinning pretty rapidly and hitting chunks of ice that are the size of a car. So when was the last time you were swinging something around and hit a car and just kept going straight through it? It's a really tall order. And so all of the propellers for an icebreaker are extra strengthened. They have a lot more weight and mass to them to handle breaking through chunks of ice. Plus, they normally carry spare propeller blades on the deck of the icebreaker. Because when you're talking about an icebreaker, your propellers are not just there for propulsion. They're also a blender for clearing out and chopping up the ice. Modern icebreakers take this one step further, using azipod propellers. Azipods use electric motors, and they can rotate the propeller in any direction in a 360-degree circle. This grants the icebreaker unparalleled maneuverability. Forward, backward, sideways, spin in a circle. The azipod icebreaker does it all. Even better, we come back to that issue of clearing ice. The prop wash can now clear the ice in any direction. Just point and clear. You can even take 2 props, split them going out sideways, and use their wash to widen a channel. It allows the ship to clear channels larger than its own beam. That makes for a far more productive operation, and it reduces the chances that the icebreaker will get stuck. Yeah, I bet you didn't think that could happen. Even icebreakers can get stuck in ice. The ice is driven by wind pushing in on the icebreaker, and it's got freezing temperatures, constantly rebinding things together. That channel might close behind the icebreaker. Remember, these channels are miles long. It takes days for an icebreaker to cut a path. So they might find that there is no way back, or the ice might get too thick to continue up ahead. Friction will build up and it'll hold the ship in place. Well, here you are stuck in the ice. What do you do now? First, make sure that the ice can't crush you. The figure on your screen shows a cross-section of the Mackinaw's hull. Notice there's no vertical surface on that hull. The hull was built so that every section has some angle off of vertical. If the ice pushes in from the side, that force gets redirected to push upwards on the hull. This is how icebreakers ride up on top of the ice in a survival scenario. Now, it's unlikely that the ice would completely push the icebreaker out of the water, but even to a partial degree, that's what's happening to relieve the pressure. This hull shape acts like a safety valve. It limits the maximum pressure that can happen on the hull. So that's survival taken care of. But ideally, we would like to keep going and to get ourselves unstuck. The Mackinaw employed a second trick to deal with ice on the sides. And this is one of their main concerns, is buildup from the sides and the friction that causes. The ship had massive ballast tanks on the port and starboard sides, and truly epic pumps connecting them. I'm talking a pump that's probably as tall as my head and 3 or 4 times as long. Massive power. Those pumps could shift thousands of gallons of water between the port and starboard tanks in a matter of minutes. We're talking about moving an Olympic swimming pool from left to right in a couple minutes. That huge shift in weight heels the ship over. Repeat the process now, pumping from one side to the other, and now you're rocking the ship back and forth. Remember, the hull is wider on the top than the bottom, so this rocking motion pushes the ice out on the sides. It also breaks free of any friction or frozen ice chunks. And this is how they get unstuck. All hail the icebreaker! Such a great and miraculous thing! Well, not completely. See, I can't sing praises for icebreakers all day. They do have a critical problem. You see, all of the features that make that hull good for icebreaking also make it terrible for open water. We want a curved cross-section on the hull to prevent the ice crushing. But that also leads to terrible rolling motion with any waves in open water. We want a wide, flat bow to crush the ice. But flat bows don't cut through waves. They bounce over waves. Not a pleasant ride. There are even stories where the big, strong icebreaker had to take shelter from a little tiny summer storm because the motions were too severe. People were falling off of their feet and hitting their head. Modern technology tried to get around this. Some icebreakers solve this problem by using the stern of the boat for their icebreaking. With the introduction of azipods, it's now much easier to drive the ship in reverse and still keep good control. Some icebreakers design the bow for conventional waves with a nice pointed front, but then the stern does the icebreaking. This eliminates some of the problems with sea motions, but that is a compromise. The biggest behemoths, the massive titans of icebreakers, they still use the bow for icebreaking. An icebreaker is at home in ice. They are hoping to find an ice pack, because it sure beats the open sea. So let's summarize everything up. First thing to think about with icebreaking is a lot of your concern focuses on the friction of the ice pushing along the sides of your hull. That's one of your primary enemies, not as much the breaking at the bow, because we have a giant massive wedge at our bow, and that's how we break the ice. We use that wedge to ride up on top of the ice and crush it from above, and that works quite well for any application. But once we've crushed that ice, it's now sitting underneath our hull, so we need a quick way to clear it out and push it away from our hull. That's where the prop wash comes in. And we took that a step further with modern technology using azipods, which are just wonderful. They're probably the best advancement we've had in icebreakers in recent years. But still, all of this has to be strengthened to handle the ice. And to take it back to the Mackinaw, this is the part that amazes me the most, is despite all of these massive advances in technology, the principles of icebreaking have changed very little. The best method still turns the ship into a giant wedge, drive the bow on top, crush the ice from above. So whether you're using old technology or refinements from the modern age, it's still the same principle involving a titan of engineering and ramming the ice. Thanks very much. I am Nick the Naval Architect. And if you want to support this channel, tell a friend about it and subscribe.
I am Nick the Naval Architect.
You know, it's like when they say I am Groot, only all we can say is I am Nick. So are you wondering where all of the knowledge and information for these videos comes from? That's actually my primary job, working as a consultant at DMS, where we are data-driven. We dig into the deep facts so that we can find the exceptions and create added value for you. If that's something that you're interested in, if you're looking for added value and a little extra edge, give us a call, check out the website, and let's see how we can make your ship exceptional. Thanks.